Good morning, everyone, for the last day of the Diff-in-diff marathon. So yesterday we had started discussing designs where the treatment is binary and absorbing, but we have variability in the timing of the treatment. And we had seen that in that case, two-way fixed effects estimators, be it the static or the dynamic one, can have undesirable properties. And that's going to lead us to consider alternative estimators, which we are going to call heterogeneity-robust Diff-in-diff estimators. What this means is that those are estimators that rely on a parallel trends assumption, like the two-way fixed effect estimator, but that remain robust if treatment effects are heterogeneous, unlike the two-way fixed effect estimators. So first, let me introduce a new set of target parameters. So remember that we have our group-specific effects, we have the more aggregated ATTL effects, and then we have the even more aggregated ATT effect. We are going to introduce some new target parameters that are going to lie somewhere in between the group-specific and the event study effects ATTL. Those are going to be cohort-specific event study effects. So in a design with variation in timing, you can actually group the individual groups into cohorts depending on the time period where they adopt the treatment. So capital C is going to denote the set of adoption dates and the set of dates such that there is at least one group that becomes treated at those dates. We're going to have underline F, which is going to denote the first date when there is at least one group that becomes treated. And we're going to let, for every cohort and time period, we are going to let Y bar CT. Y bar CT is going to denote the average outcome at period T in adoption cohort C. And so at the last time period, the cohort that adopted at C has been exposed to treatment for T minus C plus 1 periods. And so the target parameters those intermediate target parameters that have been introduced by Callaway Santana and Sunan Abraham are those cohort-specific effects of having been treated for L period. We're comparing the average outcome of cohort C at C minus 1 plus L, having been treated for L periods. So that counterfactual outcome is actually the actual outcome in cohort C at C minus 1 plus L, to the counterfactual that would have happened without any treatment from period 1 to C minus 1 plus L. So there is, of course, a connection between our ATTL event study effects and those cohort-specific event study effects. You can show that actually the overall event study effects are just a weighted average of the cohort-specific ones across adoption cohorts. So to unbiasedly estimate the effect of L periods of exposure in cohort C, for now, we are going to assume that we have some groups that are never treated, okay? And we will denote Y bar NT, the average outcome of the never treated groups at period T. And so to estimate this effect here, the estimator that's proposed by those two papers is this Diff-in-diff estimator here, which compares the C minus 1 to C minus 1 plus L outcome evolution in cohort C and among the never treated groups. So the idea is just we take the last period before period C gets treated. That's going to be our baseline. And then we compare outcome evolutions from the baseline, the last period before adoption, to L periods after adoption in cohort C and among the never treated. And we can show that under our no anticipation and parallel trends assumption, this estimator is indeed unbiased for this treatment effect. So intuitively, why is it that unlike those the two-way fixed effects estimators we had seen earlier, this estimator is unbiased for this effect under no anticipation and parallel trends assumption alone, but without having to assume that the treatment effect is homogeneous?
I think it focuses on this. It focuses on a specific group, like the non-treated, never treated, while the other one was capturing a bit of everything.
Yeah, exactly. So you remember in our numerical example with two groups and 3 periods, the early and the late, the two-way fixed effect estimator was using two types of diffs-in-diffs. One that was comparing a switcher to a never treated, which is exactly what this estimator is doing. And another diff-in-diff that was comparing a switcher to an always treated. And the negative weight issues, etc., were coming from the second diff-in-diff. To avoid this problem, we are just going to avoid leveraging comparisons of a switcher and an always treated group, which is exactly what this estimator is doing. So once we've unbiasedly estimated our building blocks, the cohort-specific event study effects, well, to estimate the aggregated event study effects, we can just follow this formula. We know that the aggregated event study effects are a weighted average of the cohort-specific ones. So we can just plug in our unbiased estimator of the cohort-specific event study effects, and that will give us an unbiased estimator of the aggregated event study effects, which is what we're doing here. And finally, to unbiasedly estimate the most aggregated parameter, the ATT, we use again the fact that the ATT is just an average of the event study effects. We plug in our unbiased estimators of the event study effects in the formula for the ATT, and that's going to give us an unbiased estimator of the ATT. So we can prove the building block, the result for the building block estimator, because it's actually not very difficult to prove. So we start from the definition of the estimator, and we're looking at the expectation of this thing. Then we realize that in a binary and staggered design, and by the definition of the cohorts, this is the outcome of cohort C before it gets treated. So it's the never treated outcome of cohort C at date C-1. And here we're looking at the never treated group. So those two outcomes are also never treated potential outcomes. There is just this one here that's actually an outcome with treatment, an outcome in the counterfactual where you're untreated for C-1 period and then treated for the L periods after that. Okay, so that's how we go from here to here. Then we do our usual trick of adding and subtracting an untreated counterfactual outcome. So here we're going to be adding and subtracting the untreated outcome of cohort C at C-1 plus L. And then why is it that we can go from here to here? So which assumption are we using to go from here to here? So this thing here is comparing the counterfactual outcome evolutions without treatment of cohort C and of the never treated cohort. Yes. Yes, and that's the common trends assumption. Okay. Under the parallel trends assumption, the cohort C and the never treated cohorts would have experienced the same outcome evolutions from C-1 to C-1 plus L. So those two quantities cancel out. Okay. And here we're just using our definition of this treatment effect for cohort C, L periods after treatment. It's been defined as exactly this expression here. Okay. So you see, it's always a bit the same. We're repeating the same proof again and again in Diff-in-diff, which might be the reason why econometricians sometimes find a Diff-in-diff a bit boring. We just add and subtract a missing counterfactual outcome, and then we use the parallel trends assumption. Okay, so we had also seen that the two-way fixed effect estimators, they have another issue, which is that in the event study regression, the pre-trends coefficient might be misleading if treatment effects are heterogeneous. We can very easily solve that as well by proposing an heterogeneity-robust pre-trends estimator, something that will really allow us to test the no anticipation and parallel trends assumption, even if treatment effects are heterogeneous. And to do that, we are going to construct a symmetric estimator to this one here. So this one here is comparing the C-1 to C-1 plus L outcome evolution of cohort C and of the never treated cohort. Well, we're going to do the same thing, but we're going to compare the outcome evolutions of the same two cohorts, but before treatment, okay, from C-1 to C-1 minus L. So it's a bit weird. In a normal Diff-in-diff, we go from the past into the future. Here we go from the future into the past, but the idea is exactly the same. We're comparing the outcome evolutions of the same two cohorts over the same length of time. Okay. So once we've done that, and so here, notice that we can do that only for adoption cohorts that adopt at period 3 at least, because if you adopt at period 2, we cannot compute an outcome evolution for you before you adopt treatment. And we can only do that for L's such that L is lower than C-2, because if L is greater than that, then you're going to be trying to compute an outcome before your data even starts, so you won't be able to do that. So with that in mind, if we want to mimic our estimator, not of the cohort-specific effect, but of the aggregated event study effect, if we want to have a placebo, a pre-trends version of the aggregated event study effect, what we can do is we aggregate all those cohort-specific pre-trends estimator, and we can do that for all the cohorts such that they adopt at least at period L plus 2. Okay, because if you adopt at least at period L plus 2, then I can compute one of those long differences for L periods before you adopt. So now there's going to be, in terms of, so the only difference between the actual event study estimator and the pre-trends one is that we have compositional changes. Okay, we don't have exactly the same groups included in the event study estimator and in the pre-trends estimator, because you're going to have groups that reach their health period of exposure to treatment after period T that cannot be included in the actual event study estimator because you don't observe them after L periods of exposure to treatment, but they might be included in the placebo estimator. And conversely, groups that adopt the treatment before period L plus 2, they might be included in the actual event study estimator, but you can't include them in the placebo estimator. But up to those small differences, this is really an estimator that's mimicking as much as possible the actual event study estimator. And if you really want to have a placebo and an event study estimator that are that exactly mimic each other, you can just restrict the estimation sample for the event study estimator and for the placebo to be exactly the same. The only caveat in doing that is that you're going to lose power because you're going to reduce the sample size. Okay, and so it's possible to show that under the no anticipation and parallel trends assumption, the expectation of those estimators is equal to 0. So we have a testable implication of no anticipation and parallel trends. Remember that we have a testable implication, but the assumptions are not fully testable. The fact that trends were parallel before treatment does not necessarily mean that trends would have kept being parallel after treatment, but assessing pre-trends is a bit the best or the least bad thing we can do to assess the plausibility of our assumptions. And to test those assumptions, we're going to test if the coefficients are significantly different from 0. And of course, because we might be testing that many coefficients are jointly equal to 0, we want to run an F-test, for instance, to account for multiple testing. And unlike the two-way fixed effect event study regression, those pre-trends estimators are robust to the validity of this test of the no anticipation and parallel trend assumption does not rely on homogeneous effect. Okay, so now let me introduce an interesting numerical equivalence. So to compute the event study and pre-trends estimators, you can do it by hand, following these Diff-in-diff equations here, computing the 4 averages and taking the differences. Or you can do everything in one go by running the following regression. You're going to be regressing YGT on group fixed effects, period fixed effects, and those relative time indicators here. So you see this regression really looks very much like the canonical two-way fixed effect event study regression. But the key difference is that the relative time indicators are actually interacted with the adoption cohorts. So you have one set of relative of indicators of relative time since adoption per adoption cohort, while in the canonical regression you have only one set of relative time since adoption dummies. Okay, so here you have many more dummies for relative time since adoption, because let's say if you have 3 adoption cohorts, then you're going to have 3 sets of relative time since adoption. And actually, so it's the paper by Sun and Abram that shows that those estimators can be computed by this regression. So a small thing to keep in mind is that, unfortunately, so, because people like applied researchers like to run regression, so they prefer running regressions than computing things by hand. And a caveat of this numerical equivalence is that in many cases, you're going to want to have control variables in your estimation. And unfortunately, if you throw in some control variables in this regression, now the coefficients, the coefficients on the relative time indicators are no longer equivalent to 2x2 diffs-in-diffs. And then they are not guaranteed anymore to identify average treatment effects under no anticipation and parallel trends assumption. Okay, so now we're going to review a number of extensions of the baseline Callaway-Santana and Sun and Abram estimators. So far, we've been assuming that we have never treated groups, but that's not always the case. And Callaway and Santana, they propose estimators very similar to those we just saw, except that instead of using the never treated cohort as the control group, they propose to use any group that's not yet treated at the time period where we try to estimate the treatment effect as the control group. So that means that in this estimator here, we're trying to estimate the treatment effect for cohort C at date C-1 plus L. Well, instead of using the N cohort as the control group, we could use the NYT, the not yet treated, at C-1 plus L. Because in the proof of theorem 11, all that matters is that for the group that we use as the control group, the observed outcome at both dates, at C-1 plus L and at C-1, is a never treated potential outcome. And then all the rest of the proof will go through. So if we use the not yet treated at C-1 plus L, for them, we still observe a never, under our no anticipation assumption, we still observe a never treated potential outcome at that date. And then the rest of the reasoning goes through. So that's an important extension for a number of reasons. So the first one is that you're going to have many applications where you don't have a never treated group. So the previous estimators are not going to be applicable anymore. So then you really need to use the not yet treated. Then the second reason why that's a potentially interesting extension is that you have cases where you do have never treated groups, but researchers are actually a little bit reluctant to use them in their analysis because they feel that the parallel trends assumption is going to be less plausible if you include the never treated. The never treated might be more different from everyone else than a group than the difference between a group that started getting the treatment at period 2 and another group that's, also started, but just 2 periods later. And so in some cases, you see applied papers where they have plenty of never treated groups in their data, but they choose to discard them and focus their analysis, leveraging only the variation in treatment timing. Now, I think our recommendation is to be a little bit careful when doing that, because doing that can lead to pretty big power losses, especially if you have lots of never treated groups. So I think you should only do that if you have strong evidence that pre-trend estimators are large and statistically significant with the never treated, and they become much smaller and much less significant when you drop the never treated from the analysis. In that case, that's a reasonable thing to do. But otherwise, maybe you just want to check for that before implementing this estimation strategy. And now the third reason why having the possibility to use not yet treated as the controls is a nice improvement is the fact that even when you in terms of identification, you're not particularly worried that your never treated would violate the parallel trends assumption. It is still the case that using both the never treated and the not yet, using the overall group of not yet treated as the control group can give you more precise estimators with a lower variance, just because that gives you a bigger control group that's going to contain more units. Now, there is one potential argument against, so we've seen many arguments in favor of using the not yet treated as the control. What could be, is there one argument you can think of that would actually lead you to prefer using the never treated only as the control group?
Yes.
So to have a stable control group, which is going to make estimate. So for instance, the fact that the control group is stable in the regression is what allows the regression formulation of the estimators with the never treated as the control group. Recently, we're going to discuss that briefly. There is one paper that found a way to express an estimator with the not yet treated as the controls as a regression estimator, but it was much less obvious to figure it out. It's a more recent contribution. But here this is, let's say, so here this is just out of convenience, out of computational convenience to fasten computation, which is not, like we discussed, when you have very large data sets, it's not a consideration we should ignore, but more in terms of the properties of the estimators. So estimators with never treated might give you a bit more robustness against a violation of one of our assumptions. Yeah, exactly. The no anticipation assumption. Okay, if you're worried about anticipatory effects and you're not in a setting where you know exactly the date when the treatment was announced to each adoption cohort, because in that case, you can just immunize your estimators against anticipation effects by redefining the treatment as the announcement date. Then you can worry about anticipation effects. And in that case, using the never treated might give you a better control group because those groups, presumably, it was never announced to them at any point that they would get treated. And so they have no real reason to react. Okay, and so when there are no never treated groups, Sun and Abram, they don't propose to use the not yet treated. Because for the I don't know if that's the only reason, but one of the reasons is because doing so would preclude them from, having this nice regression formulation of the estimators, because now the control group changes over time. But instead, they propose to use the last treated cohort as the control group. One caveat with this strategy is that the last treated cohort might be quite small. And in that case, the estimators are going to be quite noisy. Okay, so another important extension is that Callaway and Santana, they propose estimators that rely on a conditional parallel trend assumption. So they propose a principled way of incorporating covariates into the analysis along the lines of what we discussed yesterday. So they essentially just generalize estimators with covariates in the 2x2 design where you have no variation in treatment timing to the case where we have a variation in treatment timing. Okay, so some other estimators. So in the case where we have a staggered design with a binary treatment, so in this paper with Xavier, we were not necessarily we are focusing on more general designs, but in the special case of a binary staggered design, the DID-M estimator we had proposed in that paper is actually identical to the estimator of the effect of one period of exposure to treatment using the not yet treated and that of Callaway and Santana. And then in a follow-up paper, we've built upon in the follow-up paper that I'm going to present actually this afternoon, we build upon those two papers to propose event study estimators that you can use in general designs where the treatment can be either non-binary or non-absorbing. Of course, these estimators can also be used when you have a binary and staggered treatment. And then, at least in some special cases, for instance, if you don't have weighting or a balance panel, I don't think the way we deal with weighting and imbalance panels is exactly equivalent to the way Callaway and Santana do it. But other than that, the estimators in that follow-up paper are essentially equivalent to the estimators of Callaway Santana with the not yet treated as controls. Okay, so inference. So actually, there is no inference result in the Sun and Abram paper, maybe because they have this regression formulation of their estimators, and then they say they can just, rely on asymptotic results for OLS regression estimators. But because Xavier and I and Callaway and Santana were not lucky enough to have a regression formulation of our estimators, we had to do inference. And so we propose, in the two papers, we have, there are like confidence intervals that rely on asymptotic approximations. where the number of groups has to go to infinity. And under the assumption that groups are independent. So it's very much in line with the framework for statistical inference we outlined at the very beginning. So a slight difference is that the confidence intervals that we propose are valid conditionally on the design, while those of Callaway and Santana are valid unconditionally. Now I want to highlight that there is not that much simulation evidence about the finite sample coverage rate of those confidence intervals, either for our paper or those of Callaway and Santana. So we've done a bit of simulation. So we have like a technical paper that's a companion paper to our Stata package, DID multiple GTD, where we did some simulations, first internally to make sure that we had coded the variances correctly, but then to also show that the coverage rate seemed to be okay. And we have one simulation exercise that's based on a real data set where we find that the confidence intervals have close to nominal coverage with as few as 15 treated and control groups. So it's simulation based on a real data set. So, it's not completely made up simulations. Now, I'm pretty sure that you can find other settings where coverage can be actually quite bad with 15 treated and 15 control groups. So at this stage, we think that more research is needed to assess the coverage rates of those confidence intervals with small samples. At this stage, we're just going to keep the same recommendation as in the case without variation in treatment timing, which has been much more, there is much more, simulation evidence for that case. And we recommend that if you're going to use this type of confidence intervals with less than 40 treated and 40 control groups, then you should perform simulations tailored to your own data to verify the coverage rate of those confidence intervals. Because, again, you might be in a nice, well-behaved case like the one I was mentioning here, where you're fine. You don't need to worry about the coverage rate, but you could be in an adversarial case where actually the sample sizes are too low to rely on asymptotic approximations. Now, the bad news is that in the case without variation in treatment timing, we've seen that, we've not seen that, but if you're interested, you can check out the textbook on that there's been lots of methods proposed to deal with cases with few treated or few controlled. The most famous one is the method by Conley and Tabor. Unfortunately, those methods have not been developed yet have not been extended yet to the case with variation in treatment timing. I know that some people are working on it, but it's not been done yet. So what that means that if you have less than 40 treated and 40 control groups, you run simulations to assess the coverage rate of either those confidence intervals or those ones here, and you find that the coverage rate is actually not very good. Then you don't really have any alternative at this stage. Okay. And the last thing I want to mention is that the issue of having a few treated or few control groups might be especially relevant when you start looking at these very, very disaggregated effects, the cohort-specific effects. And that's why, maybe there's going to be contexts where you have very large samples and the cohorts are very large, where it's interesting to look at those cohort-specific effects. But I want to caution a bit researchers, typically like in the canonical case, which is the case where your groups are the 50 US states, you're never going to have a large enough sample size to investigate cohort-specific effects. Yes?
I have a question. So for control groups and cohorts here, you're talking about different things. So inside a cohort, you might have many controls, right?
So here I'm a bit loose as to what I mean by how many treated, how many controls. So yes. At the cohort level, it's well defined. The number up. What I mean by that, maybe I should actually introduce the notation. At the cohort level, it's well defined. It's, for instance, so if you use this estimator, then the number of control groups is the number of groups in the never treated cohort, and the number of treatment groups is the number of groups in cohort C. And then you can aggregate across cohorts. Okay. And aggregating the number of treatment groups is easy because the cohorts, they don't overlap. So you just sum the number of treatment. So in your ATTL estimator, you just count the number of treatment groups in each of the cohort C. For here actually it's easy because if you use this estimator, the number of control groups is the same for so you don't aggregate there. It remains equal to the number of never treated groups. For the if you use not yet treated, yeah, it's a bit tricky because the number of control groups is largest for the effect of one period of exposure, but then it declines. So what's going to be the good concept actually? Is it like the average number of control groups across all the exposure lengths you're looking at? Yeah, maybe it's worth adding a few lines on. I mean, I don't think there is a, like here all I do at this stage is just propose some kind of rule of thumb, but I think it's an interesting question to explore. Yeah, maybe let me quickly make a note of that. Okay. And yeah, so a recent development is one more estimator that I quickly mention by Dubé and co-author, who propose what they call a local projection estimator. Essentially, they found a very clever way of obtaining the estimators with the not yet treated as the control group via a regression. And the regression is you regress the long difference of the outcomes on period fixed effects and the treatment change, restricting the sample to GTs that are either such that G becomes treated at T or G is not treated yet at T-1 plus L. And so actually to be fully specific, this is actually not going to be exactly equivalent. Instead of estimating the effect of L period of exposure, it's going to estimate some kind of variance weighted average of cohort specific effects of L period of exposure, similar to the result in Engris 1998 for those who are familiar with this type of results. But by undoing the variance weighted averaging inside the regression, you can then actually recover exactly the Callaway-Santana estimator. And here, the estimators are numerically equivalent. So in principle, in terms of their properties, bias, variance, etc., this formulation is not bringing anything new. Computationally, that can be very helpful, especially because the way the Callaway-Santana command is coded, for some steps, it relies on the bootstrap, so it's a bit slow. So this can give you, if you want to use one of the estimators in let's say, the Danish registry data where you have millions of observations, maybe it's going to be useful to use this formulation of the estimator. Okay. Yeah, so let me skip that. Okay, so the Stata and the R command. So the estimators of Soon and Abraham, they're computed by the event study interact command, whose syntax is outcome. Then you put your relative time indicators exactly as you would in an event study regression to indicate how many event study effects you want to compute and how many pre-trend estimators you would like to see. Then you need to indicate an identifier for the group variable, time identifier. You need to construct a cohort variable that indicates the date at which each group starts receiving the treatment. And then you need to indicate to have a dummy for the control group, which can either be the never treated or the last treated cohort. So yeah, and there is a subtlety about how you indicate in the cohort variable how you should, but yeah, maybe we'll see it before because they don't. Not all commands have the same convention for the never treated. Some commands require that the never treated have a missing of the cohort variable, while other commands require that that they have a 0. And, if you don't pay attention and you try to compare all the estimators, at least in our case, that led us to at some point have an incorrect version of one of the estimators. Okay, so the estimators of Callaway-Santana, so it's they're computed by the CSDID command and by the DID-R command. So the syntax of the Stata command is CSDID outcome, and then you just have the time variable and then the cohort, the adoption cohort variable. And those estimators are actually also computed by official Stata functions that I'm mentioning here. And finally, our estimators, they're computed by the DID multiple GTDIN Stata command. And same thing for in R. And the syntax of the Stata command is DID multiple GTDIN outcome group time treatment. And then you need to specify how many event study effects you want to see and how many placebos you would like to see. Okay, so now let's apply this to the UDL, the unilateral divorce law example. I would like you to start by computing the estimators of Sun and Abraham using the never treated groups as the control cohort. And you should, okay, so that's here where it said, you should pay attention to the fact that in their command, the cohort variable has to be missing for the never treated groups. Okay. Good. So are you getting very different results from those you were obtaining earlier with the canonical two-way fixed effect event study regression? Okay, so I start by fixing my cohort variable, and then I run the command. So event study interact the outcome, or so I want to see 16 event study effects and 8 or and 9 placebos. So I just put in all my relative time indicators. I weight, as I, following Wolfers and Friedberg, I weight by population. And then I indicate my group level variable and my year variable, my treatment cohort variable, and the control group are going to be the never treated. And I cluster standard errors at the state level. Okay, and so when I do that, you can see that things look a bit similar to what we had in the canonical event study regression, namely, so we have a positive effect at period 1, so it's very noisy, like was the case for the canonical estimator. At period 2, the effect is still positive and significant, etc. And then it becomes still positive but less significant, and then in the end it becomes actually negative and significant. And the placebo estimators are small and insignificant. Okay, so the picture is not very different, and actually if we put those on a graph where it's going to be more compelling visually. So that's the two-way fixed effect estimators. That's the Sudan-Abraham estimator. So you see that the differences are not very large. So the fact that the differences are not very large could be due either to the fact that the effect of those unilateral divorce laws are not very heterogeneous. That could be a possibility. Even though it's not shown here, but we run a few tests, and for instance, we find that the treatment effects seem to be very correlated with the state's population, with more populated states having much larger effects than less populated states. Maybe, yeah. So maybe the story could be more populated states are more liberal, and when the law is passed, you have many couples there that divorce, while in more conservative states, even after the law, people don't divorce. You could have stories along those lines. So the effect seems to be heterogeneous. So then a second possible explanation is that, like we saw, the issues with negative weights, the issue with contaminations were not that pronounced in this case. So maybe heterogeneous effects don't bias too much the canonical regression. Okay, so then we are going to implement the estimators of Callaway and Santana. And to do that, so we need to be, that's where, you need to be a bit careful that for them, if you're never treated, then cohort has to be equal to 0. And then I implement CSDID, divorce rate, I weight, the group variable is the state, and the time is the year, I have my cohort. I want to use the not yet treated as the control group, because otherwise that would be numerically equivalent to Sun and Abraham. And so their command allows you to have estimators at various levels of aggregation. You could want to get the ATT, you could want to have the ATTL or the cohort-specific event study effects. Here I'm asking for ATTL estimators of the event study effects via this AG event option. And so you see, that's what I was mentioning. The small dots correspond to the fact that this command is using the bootstrap for inference, and that's why it's a little bit slower than the others. Even though, in a small data set like this, it's not a big deal. It still runs in a few seconds. It's only if your data is very large that the command can become a bit slow. So if we go to the event study graph, you see that again, if we look at the right-hand side of the graph, the event study estimators are again very similar to two-way fixed effect and Sun and Abraham. Interestingly, the confidence intervals are not noticeably smaller than for Sun and Abraham, okay? Which means that using this bigger control group, the not yet treated, in this case, that does not seem to lead to a major gain in precision, which could be because we have many never treated states in that application. We have, if I'm remembering correctly, we have 21 out of the 50 states that are never treated. So adding a few not yet treated to the control group does not seem to increase precision massively. Something I did not note is that there is, so here, everything is a bit, when it comes to variances comparisons, everything is a bit against what you would expect. So Callaway-Santana does not lead to more precise estimators than Sun and Abraham. And similarly, the heterogeneity-robust estimators do not lead to less precise estimators than the two-way fixed effect event study regression. If anything, it's a bit the opposite, which typically is a bit, you would expect that, a more robust estimator typically is less precise. And it's probably, this application might be a bit specific on that dimension. I think on average, actually there is some political scientists have made a meta-analysis comparing two-way fixed effects and heterogeneity-robust estimators. And they tend to find that the heterogeneity-robust estimators on average have higher variances. The difference is not as large as I would have expected. On average, the standard error is 10% larger for the heterogeneity-robust than for the two-way fixed effect one. But still, there is a precision loss. But it's not always true, and this application is an example where it's actually more the opposite. So the last thing I wanted to comment on in this graph is that where the Callaway and Santana estimators do look very different is on the left-hand side of the graph, okay? And in particular, it would seem like the confidence intervals for the pre-trained estimators are much tighter than with two-way fixed effect and Sun and Abraham. This is just an artifact that's coming from the fact that the Callaway and Santana pre-trained estimators, they are first difference pre-trained estimators. So those ones here, they're comparing so for instance, for this one here, so for the first one, it's not going to matter, but starting at the second one, this one is going to compare the outcome evolutions from the date before adoption to 3 periods before adoption, so over 2 periods between the treated and the controls, while this pre-trained estimator is going to compare the outcome evolutions of the treated and the control between 2 consecutive periods, namely from 2 periods to 3 periods before adoption. And here, because the fact that the variances seem to become much larger when we look at longer horizons, that could, for instance, be compatible with a model where the DGP is a random walk. For the errors for the outcome are a random walk, whereby the noise accumulates when we look at longer and longer horizon, and that would then explain why those confidence intervals are much smaller than this one. And in fact, there is Jonathan Roth has a recent note where he recommends, and I think it's a good recommendation, to not use first difference placebos and always use long difference pre-trans estimators. The rationale being that otherwise, the magnitude of those differential pre-trans estimator is not comparable to the event study estimator. So with, like the type of reasoning that applied researchers often make, they say, okay, so this here is giving me a proxy for the bias that I might have in this event study estimator number 3 caused by differential trends. So you see, I see that over 3 periods before treatment, I had differential trends of this magnitude. So maybe this estimator here is a little bit biased, but the bias should be of this magnitude here. Well, this type of heuristic reasonings is not applicable anymore with this type of pre-trend estimator, because this is just looking at differential trends over 1 period, while this is comparing differential trends for 3 periods. Okay, so that's the rationale for using long difference placebos. So the Callaway-Santana Common, they have an option to get long difference instead of first difference placebos. But here, I'm just following the default version of their command, which returns first difference placebos. Okay. So, and then if you want to use our command, the syntax is going to be the same, is going to be this one here. And they're not reported on the figure, because even though due to the weight, due to the weighting, and the fact that the panel is a bit imbalanced, they are not numerically equivalent to those of Callaway and Santana. They are still very close, because here it's a binary and staggered design, so we don't show them on the figure. Okay, so that's the first family of heterogeneity-robust estimators for binary and staggered designs, which are simple diffs-in-diffs estimators. Now we're going to discuss a second family of estimators that are called imputation estimators, that we've already discussed in the classical Diff-in-diff design, because there as well, you could already make a distinction between diffs-in-diffs and imputation estimators. And those estimators, in the context of diffs-in-diffs, or in the context of two-way fixed effect model, have been proposed by Borusiak et al., Gardner, and Liu et al. And I'm going to focus on the Borusiak et al. Paper, but you need to keep in mind that those two papers had proposed the same estimators at about the same time. So there's going to be several numerically equivalent ways of obtaining those estimators. So a first way is to run a two-way fixed effects regression of YGT on group fixed effects, time fixed effects. But then instead of having just one coefficient in front of the treatment variable, we actually have we actually put dummies for each of the treated GT cell, and each dummy is going to have its own GT-specific coefficient in front of it. And so to estimate the treatment effect in cell GT, we're going to use the coefficient in front of the fixed effect for the treated cell GT. Then once we have these coefficients, of course, those, those are estimators of treatment effects that apply to only one unit. So they might be unbiased, but they will never be consistent, asymptotically normal, etc. So we need to aggregate. But then once we have these building block estimators, it's very easy to aggregate. We can aggregate them across cohorts and lengths of exposure. We can aggregate them only across lengths of exposure, or we can have a fully completely aggregated estimator of the ATT. So it's possible to show that those estimators are indeed unbiased under the no anticipation and parallel trends assumption, and therefore those are heterogeneity-robust estimators. So intuitively, why is it that those estimators are robust to heterogeneous effects?
They are really specific. Hasta que los contiene specific effects. What the ordering of the GPs that otherwise bias the rushing the language these specific effects.
Yeah, exactly. So we saw that by having just one coefficient in front of the treatment variable, the two-way fixed and the coefficient was not indexed by GT. The two-way fixed effects regression was implicitly assuming constant effects. So in some sense, it should not have been surprising at all that this regression would be not robust to heterogeneous effects. The surprise actually only came from the fact that in the context of cross-sectional models, in an RCT, if you run a regression of an outcome and an intercept and the treatment, there as well, you have a treatment coefficient that's not indexed by I, the units in front of the treatment. And yet, even if you have heterogeneous effects, the coefficient is consistent for an average treatment effect. But this is more an anomaly, if you will, than the norm. And in a panel data context, the implicit assumptions made by the regression model actually apply. And to relax those assumptions, one way of doing that is just by interacting is just by having a regression model where now we have a coefficient in front of the treatment that's now GT specific, which is exactly what this regression is doing. Yeah?
How is it different from anatomy?
Okay, maybe let me move to the second numerical equivalence, and then the difference is going to become a bit clearer. Okay, so there is this result by Wooldridge, who shows that if you're interested in estimating the cohort-specific event study effects, then a numerically equivalent way of getting the same estimators as the Borusiak et al. Paper is by considering this regression here, where instead of regressing YGT on G fixed effects, T fixed effects, and a dummy for every treated cell, we can actually have a much more parsimonious regression model where we only have cohort-specific, where we only have cohort fixed effects instead of the group fixed effects, time fixed effects, and then we interact cohort of adoption fixed effects with relative time since adoption fixed effects, but we only include relative time after adoption, not relative time prior to adoption. And that's the difference with the Soon and Abraham specification. Okay, this specification is exactly the same as the Soon and Abraham specification, except that you don't have the cohort prior time prior to adoption fixed effects. Okay, and finally, a last numerical equivalence is the so which we already saw actually in chapter 3. So yeah, so also this formulation makes it clear that if you don't have variation in treatment timing, then the Borussia et al. Estimator is numerically equivalent to the estimator we discussed in chapter 3, which was the canonical two-way fixed effect event study regression without variation in timing, except that instead of having fixed, relative time after adoption and prior to adoption, you were just dropping anything prior to adoption, and that led to this estimator where the only difference with the canonical estimator was that instead of using period F-1 as the baseline prior to adoption, we were using the average of all the pre-treatment periods from 1 to F-1 as the baseline. Okay. So the Borussia et al. Estimator is really a generalization of that estimator to the case where we have variation in treatment timing. Okay, and so in this chapter 3, we had seen that this type of estimators, they can a numerically equivalent way of computing them is via imputation, a two-step procedure where we start by fitting a two-way model of the outcome on group and time fixed effects, restricting the sample to the untreated. And then we use that imputation first step to predict the counterfactual outcome without treatment of all the treated GT cells. And then finally, we can estimate treatment effects by subtracting from the actual outcome of the treated GT cells their predicted outcome according to the first step two-way FE model. Okay, and an advantage of this imputation method is that because, even with very optimized commands such as reg HDFE in Stata or in R, in large data sets where you can potentially have a very large number of fixed effects, estimating models with fixed effects can take a little bit of time. So an advantage of this formulation here is that the first step, two-way fixed effects regression, does not have that many fixed effects, and so it can be a bit faster computationally. Yes?
Just a question about the imputation. If the outcome is binary, wouldn't it be natural to do it with a probit or logical set?
We're going to talk about that.
Okay.
Yeah, absolutely.
Yeah. Joe. Cool.
But perhaps a more important actually advantage of the imputation procedure is that then, like I said, an issue with the regression formulation of all these heterogeneity-robust estimators is that then when people want to control for covariates, it might be tempting to just throw in the covariates linearly in the regression. You could just, throw in some covariates here. And you can do that, but you're going to face the problem that we discussed in chapter 4, that then the version of this regression with covariates is trying to do too many things at the same time. Again, it's trying to estimate the effect of the covariates on the outcome and the treatment on the untreated outcome and the treatment effect. But because these regressions are estimated in the full sample where you also have units that are treated, the coefficients on the covariates are going to get contaminated by treatment effects, etc. And therefore, the version of this regression with covariates could end up estimating non-convex combination of treatment effects. An advantage of the imputation procedure is that if you want to control for covariates, you can do that very easily by including the covariates in the imputation first stage. Okay, and there, the coefficient on the covariates will not be contaminated by treatment effects because that first stage is estimated only in the control sample. And similarly, you can, if you want to do triple diffs, if you want to have group-specific linear trends, etc., it's very easy to do in the imputation setting. Okay, so that's an advantage of the imputation setting. Okay, and on inference, it's a bit the same message as for the Callaway-Santana estimator and our paper. So they have large sample results and confidence intervals based on asymptotic approximations. There is just not that much simulation evidence at this stage on the coverage rate of those confidence intervals with when the number of groups is not that large. And so the recommendation is the same as before to do simulations based on your own data when you have less than 40 treated or less than 40 control groups. So now a difficulty. So, once we have this regression formulation of those estimators, it becomes very easy to see that, so, in a feature that I personally find appealing with like all with the Sun and Abraham, Callaway-Santana or our estimators is that it's very easy to construct pre-trans estimators that are going to be the exact symmetric of the event study estimators, and you can actually estimate everything jointly. Here you can see that you're not going to be able to estimate jointly pre-trans and event study estimators because precisely the originality of the Borussia et al. Estimator with respect to Sun and Abraham is to actually drop all of the coefficients that are supposed to estimate pre-trans. Okay, so Borussia et al. They still propose a way to test for pre-trans, and the idea is to re-estimate the first step of their two-step imputation procedure. But what you do is that instead of estimating just, a basic two-way model with just group and time fixed effects, in the first step imputation procedure, you're going to include leads of the treatment. Okay, dummies that are equal to 1 when a GT cell that's untreated is still such that G will be treated in 1 period from now. Or if you have 2 leads, G will be treated in 2 periods from now. And then the idea of their pre-trans test is to check whether in the imputation first step, the coefficients on the leads are significantly different from 0 or not, because if they are, that indicates that groups that will get treated in 1, 2, 3 periods from now are already experiencing differential trends. So the Stata and R command that implement the Borussia et al. Estimators are the DID imputation commands. And the basic syntax is DID imputation, outcome, group, time, and the date of the first treatment. And the Gardner et al. Paper, they have a DID 2S Stata command. And Liu et al., they have a command that's called FECT in Stata and in R. Okay, so we're going to compute the imputation estimators of Borussia et al. And here again, we need to be a bit careful. For them, the cohort has to be equal to 0 for the never treated. And when we do that, again, we find pretty similar estimators as before. The event study estimators, the pre-trans are insignificant. Here you see that I normalized the event study graph at -9 instead of normalizing it at 0. And that's to reflect the fact that the pre-trans estimators are a little bit different in this estimation strategy. So to mimic I still wanted to have 9 pre-trans estimators like for the other methods. But so then in their method, that means that I need to include 9 leads of the treatment, which means that everything becomes relative to 10 periods prior to adoption, which is why I put the normalization here on the graph. Okay, so let's compare we're going to be comparing those Diff-in-diff on the one hand and imputation on the other hand estimators. And we're going to be comparing the properties of those estimators. But maybe at the end of the day, what might matter more for practitioners, because we're going to see that in terms of their statistical properties, it's not really clear that one estimator really dominates the other. And in any case, if they give you very different results, that should be a cause for concern, because that would mean that you have differential trends and no anticipation. So maybe at the end of the day, the main criterion you should choose when you decide which estimator to choose is actually the software implementation rather than the estimator themselves. So we're going to do some kind of, consumer reports type comparison of the main estimators. So, but still the statistical properties. So, you remember that under parallel trends, we can decompose our untreated outcome into a group fixed effect alpha g, a time fixed effect gamma t, and an error epsilon gt. And so Borosiak et al., they show that if the errors epsilon gt are IID, and in particular independent across both the groups and the time periods, then their estimator is the blue of the cohort-specific event study effects, which means that the variance of their estimator is lower than the variance of the estimators of Callaway-Santana and Sunana-Bram. Now, we've seen in chapter 3, we've actually already discussed this result, because we saw that the estimator we discussed there, where instead of using just f-1 as the baseline, we were using the average of all pre-treatment periods. That was actually just the Borosiak, Liu, and Gardner estimator in this context. Okay, and so there we have seen that the efficiency ranking between, and also I should say that without variation in treatment timing, the Callaway-Santana and Sunana-Bram estimators, they reduce to the standard event study estimator when we don't have variation in treatment timing. So in that chapter, we have seen that the efficiency ranking between the imputation versus diff-in-diff actually is highly dependent on the assumption we make about the errors. Because if instead of assuming that the errors are not serially correlated at all, we assume very strong serial correlation, namely we assume a random walk for the errors, then actually it's the diff-in-diff estimators that become the blue, and then the diff-in-diffs are more efficient than the imputation estimators. Now there is the question of whether, and this was a result coming from this paper by Harmon 2022. So now, do we have the same type of results in binary and staggered designs where we have variation in treatment timing? The answer is yes, up to small nuances. So we have the exact same result when it comes to estimating the effect of one period of exposure. There, the Harmon result shows that the estimators of one period of exposure that we had proposed with Xavier and Callaway-Santana, and actually not Sunana-Bram, because here using the not yet treated is actually important. That estimator is the blue if we have random walk errors. Okay. Now, when we want to estimate effects of more than one period of exposure, unfortunately, the blue is neither Borosiak et al. Nor Callaway-Santana. It's yet again a third estimator, which has this expression here, which is essentially not very different from the Callaway-Santana estimator. So remember, the Callaway-Santana estimator is going to compare the C-1 to C-1 plus L outcome evolution of cohort C and the not yet treated at C-1 plus L. Well, we can do a little bit better than that by, instead of computing one long difference, we can improve a bit by chaining first differences where the control group can be a little bit bigger than just the not yet treated at C-1 plus L in each of the first difference. So we're going to decompose our C-1 to C-1 plus L long difference into the sum of the first difference from C-1 to C, and then from C to C plus 1, and then from C plus 1 to C plus 2, etc. And now in each of these first difference, instead of only using the not yet treated at C-1 plus L, well, in the first difference from C-1 to C, we can use all the not yet treated at C. And then in the first difference from C to C plus 1, we can use all the not yet treated at C plus 1, etc., etc. And this estimator, which we're going to call a chained Diff-in-diff estimator, because we're chaining a long difference as the sum of first differences, has been proposed. Interestingly, it's always the case in this literature, independently at the same time by two papers, this paper by Bellego and co-authors, and the Armand paper that I was mentioning. And interestingly, the Bellego et al. Paper, they're not interested at all in robustness to heterogeneous effects or in efficiency. They're interested in dealing with very imbalanced panels. And in the case where a panel is highly imbalanced, this type of chained diff-in-diff estimator can be very appealing, because if your panel is very imbalanced, you're going to have very few units that you observe for L consecutive periods, so as to be able to compute the long differences required by, like the Callaway-Santana estimator, while there might be many more groups that you observe for just consecutive time periods. And they have also invented the chained diff-in-diff name, but so the same estimator has been proposed by the Armand, and the efficiency result is in the Armand paper. And so both papers have comments in Stata for the Armand paper and in R for the Bellego et al. Paper. They have packages. Now, I mean, honestly, to try it, I feel that, they have simulations where they show that you can get pretty large efficiency gains with respect to Callaway-Santana, etc. Like, to not add even more confusion to the already pretty, or to not add even more options to the already pretty big set of options that people have, I would not necessarily recommend using those estimators. I think they are very likely to give you pretty close results to those of Callaway and Santana. But, until someone proves me wrong, that's going to be my recommendation. So, So we see that when we compare the efficiency of those estimators, from a theoretical standpoint, there is no clear-cut answer. One estimator could be more efficient than the other. It really depends on the DGP. So in practice, when we look at our event study graph here, did I skip it? Yeah, I did skip it. When we look at this event study graph, does it look like, when we look at the size of those confidence intervals in this panel, and that panel, does it seem like one of the heterogeneity-robust estimator is consistently more precise, has like tighter confidence intervals than the others? No, there is really just one thing that's a bit striking, which is that for the estimated effect of one period of exposure, that estimator, for whatever reason, seems to be really more precise than, and substantially so than all the others. But actually, this reverts when you look at longer run treatment effects. And actually, the differences, even though they are less striking visually, they are pretty substantial. Like, if I'm remembering correctly, like for some of the long run effects, you can have confidence intervals with that estimator that can be up to 50% larger than those of the Callaway, Santana, Soon and Abrams. So it's in line with the theory that there is no clear ranking in terms of efficiency between the estimators. Now, okay, so variance is not going to help us discriminate between the estimators. Now, what about bias? So for bias, that's going to be the same as in designs without variation in treatment timing. The Borussia et al. Estimators are using all pre-treatment periods as the baseline, while the DID estimators, they only use the period just before treatment. So the imputation estimators, they rely on parallel trends assumptions over a longer horizon. And because of that, if you have, let's say, differential linear trends between the treated and the control, imputation estimators will be more biased than the Diff-in-diff estimators. On the other end, if you have anticipation effects, the imputation estimators could be less biased than the DID estimators. Okay, and also an important bottom line is that the two sets of estimators are unbiased for the same target parameters under the same assumptions. So if they differ significantly, that should be a cause for concern. Okay, and so I know that now referees sometimes are asking you to plot all the, like the 10, because I'm covering only a fraction actually of the, it's becoming a cottage industry to have like, your own heterogeneity-robust estimator. And referees are asking to see all of them. I don't think it's really necessary, like showing one of them to check whether it gives very different results from the event study estimators. That seems like a very reasonable advice, but showing all of them, it's not, because also then there is the idea of say, but I can use the comparison of the estimators to test non-anticipation and parallel trends. Yes, that's one possible way of testing those assumptions. But even though nobody has studied it formally, I'm pretty sure that this is going to be a much less powerful test than looking at pre-trends estimators. Even though actually that could be a way. So let me take this back, because that could be a way of testing non-anticipation and parallel trends after treatment, actually, which I don't think has been noted at this stage. But yeah. Okay, so now software implementation. So here we have this table. I'm not going to review everything, but where we do, the type of consumer reports exercise I was mentioning. We just compare we are reinforcing the oligopoly. We are only comparing those that are currently the most used, which does not mean that those are necessarily the best, but it's just that otherwise the table, which is already a bit dense, would become totally unreadable. So each package has its pros and cons. So if you look at something that's quick, the DID imputation is the one that's the fastest. And for instance, with CSDID, the differences can be pretty large. Like here, so on a small data set like the Wolfers et al., the differences are okay. So it's in relative terms, it's large, but you can wait for 9 seconds to get your results, and that's okay. But in a larger data set, which is still not unrealistically large, where you would have 5,000 groups and 33 time periods, now with DID imputation, you just need to wait for 1 minute, while with CSDID, you need to wait for more like 6 minutes. So it's a bit more substantial. In terms of applicability, and here, of course, I'm selling my own work, a big difference is that all of those packages are only applicable to the case with absorbing and binary D. The only one that's applicable when you have a non-absorbing and or non-binary D is our package. Differences that are perhaps that are interesting. Yeah, so a strength of the CS-DID package is that it's the only one that allows you to control for time invariance covariates non-parametrically in every case, even if the covariates are continuous. So all the other packages, they only allow you to control non-parametrically for discrete covariates. And if you have continuous covariates, then you can control for them, but linearly. Okay, so that's a dimension on which the CS-DID command is remarkable. And and one feature that I like to highlight is that, like all this literature, the starting point is a concern for heterogeneous treatment effects. But then it becomes interesting to actually investigate if treatment effects are heterogeneous or not. And two of the packages, the DID multiple GTD1 and the DID imputation, they have built-in options to allow you to test for heterogeneous effects. Okay. So actually, I think I'm gonna skip the extension to nonlinear models, because otherwise we won't have the time to talk about designs where you have variability in the dose of treatment. So very briefly, let me just say that Wooldridge proposes a method to have heterogeneity-robust probit or logit regression model when you have a binary treatment with variability in treatment timing. And the idea is really to extend the insights of the linear case to the nonlinear models. You just, you run a probit with cohort fixed effects, time fixed effects, and then you interact the cohort fixed effects with relative time since adoption. And that's going to give you a probit that's robust to heterogeneity. And here I should say actually that I said probit, but I should have said logit, because in this case, there is actually an advantage to using the logit regression instead of the probit one. He also proposes a generalization to Poisson. So it's same idea. You run a Poisson regression with the time since adoption fixed effects interacted with the cohorts. And then we review one more application, because you might think that when you see this event study graph, that I keep missing. When you see this event study graph, you might think, okay, so this whole heterogeneity robust for treatments with variation in treatment timing thing that was, just much ado about nothing. It's always giving you the same results as two-way fixed effects. And I think it's, that's actually something that we want to push a little bit, that sometimes it actually makes no difference at all with respect to the canonical estimators. But here we also have a second application, which where people look at the effect of bilateral trade agreements on trade. And here, using heterogeneity-robust estimators makes a big difference. You see, and interestingly, so in this literature, in the trade literature, they are obsessed with, specifications that are micro-funded by a gravity model that gives rise to, a Poisson regression specification. And so then you can do the normal Poisson regression that assumes constant treatment effects, or the Wooldridge version of the Poisson regression that allows for heterogeneous effects. And when you do that, the treatment effects change markedly. Now you're finding treatment effects that are twice as large. And this is kind of solving almost a puzzle in this trade literature, because people had, estimated those regressions for a long time, and the effects they were finding that, a bilateral trade agreement only increases trade by 17% That was kind of a puzzle while the effect was so low, like the theory was predicting much larger effect. And actually you do, when you use the correct estimator, you do find a much larger effect. And what's interesting is that if you do the naive, if you forget about all the gravity model, micro foundation of the specification, and you just run OLS, in line with a conversation we actually had at the beginning of the class. In this example, at least, I know that there are examples where using linear versus Poisson gives you different results, but in this example, you get almost the same result. On the other hand, accounting for heterogeneity is, again, quite important. Okay. So that's it. Let's take a 10 minutes break, and then we will talk briefly about designs where we have variation in the dose of treatment. Okay. So now we move to a different deviation from the classical design, where we don't have variation in treatment timing, but we have variation in the dose of treatment. Some groups we're going to have 2 periods. Some groups will get treated at period 2, but there's going to be variability in the dose of treatment received by the treated groups. And so the period 2 dose of treatment, that could be a discrete variable that takes a small number of values. You could have some units that get 1 dose, others that get 2, and others that get 3 doses, and that's it. Or it could be potentially a continuously distributed variable, where each treated group receives its own unique treatment dose that nobody else in the population receives. And because we want to allow for a continuously distributed dose of the treatment, we're going to be moving away from our model-based perspective where the treatments are conditioned upon, to adopt a sampling-based perspective where we assume that the capital G groups we observe are a random sample from an infinite superpopulation of groups. And therefore, we are going to replace our independence assumption by assumption IID. And because we assume that the groups are IID, we're going to be able to drop the G subscript everywhere in this chapter, except when we go back to defining estimators. And the reason why we introduce the infinite superpopulation is just that because we want to allow for the possibility to have a continuously distributed treatment at period 2, the notion of a continuously distributed variable requires introducing an infinite population. So formally, we're going to define heterogeneous adoption designs as follows. So D1 is equal to 0. D2, so nobody is treated at period 1. D2 is weakly positive. And then we have that the treatment dose at period 2 varies, and it also varies among the treated groups. Okay, and that's really this condition here that distinguishes an heterogeneous adoption design from a classical design. So some of our results are going to apply to a subset of heterogeneous adoption designs, namely those with stayers or quasi-stayers. So formally, that means that we assume that 0 belongs to the support of the period 2 treatment. So there's going to be 2 leading cases where this assumption holds. The first one is going to be the case where we have stayers, meaning that we have a strictly positive probability of having some units that are untreated at period 2. We have a strictly positive fraction of the population that remains untreated at period 2. And we're going to call those groups, we're going to call them the stayers, because they were untreated at period 1 and they stay untreated at period 2. Then the second, a little bit more abstract, but still relevant for some applications case, will be the case where even though we don't have any unit that remains completely untreated at period 2, we have some units whose treatment is local to 0, is arbitrarily close to 0 at period 2, meaning that for any delta, including very small ones, we will always have that the probability, the proportion of units with a period 2 treatment included between 0 and any small delta will be strictly positive. So perhaps an easier way to think of that case is to think of the density of the period 2 treatment. You know, we're all familiar with the concept of the density of a continuous random variable. And then this case with quasi-stayers will hold if the density of the period 2 treatment is continuous and strictly positive at 0. And so those groups whose treatment is local to 0, we're going to call them quasi-stayers. So the running example that we're going to be using, even though unfortunately, so the data is proprietary, so I could not give you access to it. That's something we'll need to deal with later. So we're going to be revisiting a trade paper that looks at the effect of China's accession to the WTO on US employment. You know, so it's one of those quote unquote China shock papers. And that specific paper is using the fact that when China joined the WTO, that reduced uncertainty on the trade tariffs that would apply to Chinese imports into the US. Because even before China was a member of the WTO, it already benefited from the low tariff rates that WTO members enjoyed. But it was kind of an exceptional derogatory status that had to be reapproved every year by the US Senate. And you know that the US Senate can be a little bit unpredictable. And so that means that each year there was some uncertainty as to whether those low tariff rates would be reapproved or not. And so the reform, it eliminated uncertainty on tariff rates between China and the US. So it's a bit of an abstract treatment. The treatment amounts to eliminating uncertainty on future tariffs. And the amount of uncertainty that was eliminated by the reform varies across industries because you have, so if the Senate had not voted the extension of this policy, tariffs would have gone back to some old tariff rates and that had been fixed in the 30s, if I'm remembering correctly, that varied a lot across industries. So you would have had industries where tariffs would have spiked to a much higher level because this old tariff from the 30s was very high, and industries where the tariff spike would have been much lower. And so that leads Pierce and Scott to define what they call the NTR gap treatment, which is the differential between the WTO tariff rate and the much higher tariff rate that an industry would have experienced without renewal. And they plot, they define their treatment variable as the interaction of this gap and being after 2002, which is the year when China joined WTO. No, actually 2001. And so by definition, you have that no industry is treated before, and then all industries are treated after, and actually you don't have stayers. So for every industry, there is a strictly positive amount of uncertainty that's being eliminated, a strictly positive potential tariff spike that's being eliminated by the reform. But when they plot the density of the potential tariff spikes that are being eliminated by the reform, you see that the estimated density is strictly positive at 0, which suggests that we do have quasi-stayers. We do have industries where the tariff spike eliminated by the reform, the treatment is local to 0. Okay, so we're going to be imposing our no anticipation assumption. We're going to also rule out dynamic effects. In this chapter, this is just out of convenience because we're considering a 2 periods case where everybody is treated at period 0. We could allow for dynamic effects, but it's just that the notation would become a bit more heavy. And we're going to replace our standard parallel trend assumption with a different one that's going to be better suited to the cases with a non-binary treatment we're considering, and also to the case where we have IID instead of just independent groups. So we're going to let delta x denote for any variable denote the first difference from period 1 to 2. And then our parallel trends assumption with the non-binary treatment is the following condition. Requires that the expected outcome evolution without treatment given the period 2 treatment is equal to some real number mu 0. So could you try to interpret this assumption? Yes.
Yeah, so for any value of your treatment period, so you would assume that any group would have the same level of achievement potential outcome under no treatment.
Yeah, exactly. So you assume that without treatment, the strongly and the weakly treated groups would have had the same outcome evolution.
Any different levels of the treatment. Well, not that we have other different or
No, it's not indexed by Z2. This real number is, it's constant for, yeah. And so actually this, for those of you who've studied panel data models, this is really exactly the same thing as the strong exogeneity condition in panel data models. And that's, that's an aside, but that shows that, there is obviously a very strong connection between classical panel data econometrics and Diff-in-diffs, in the sense that you can think of parallel trends and strong exogeneity as being essentially the same thing, just two different ways of saying the same thing. So a nice feature of this assumption is that you can run pre-trends test of it. When instead of having only 2 time periods, you have a third one, period 0, where everybody there as well is also untreated. Because in that case, you're going to have that the outcome evolution from period 0 to 1 is also an outcome evolution without the treatment. Okay. So actually, how would you run a pre-trends test of this assumption now that the treatment is not binary?
in this start at the same level of treatment. You just
Okay, so maybe how do people in those designs, how do people typically estimate the effect of the treatment? So you have, some groups that where everyone is untreated at period 1, and then some become treated at period 2. So which type of, regression could you be running to estimate the effect of the treatment? You're going to be...
If you have not many but possible values of the treatment or every of such values, you can separately let it in variable.
Yeah.
That's only pretty the same test.
Okay, excellent. So that's more sophisticated than what I was thinking, but that would actually be the correct way of doing it. So typically people don't do that. Typically people just regress delta y on the dose. So, they look at outcome evolution from period 1 to 2, and they run a linear regression of that on the dose. A pre-trend version of that would be to compute the pre-treatment evolution from 0 to 1 and regress it on the dose. Okay. So that's not exactly testing this identifying assumption, which that's testing that the dose and the outcome evolution without treatment are uncorrelated, which is weaker than here. What we assume is stronger. We assume that we have mean independence, and to test mean independence, that can be done if D2 takes a small number of values. Then you would just regress the pre-treatment outcome evolution on dummies for any possible value that you have a reference category, and then you have dummies for all the other values, and then you run an F-test on all those dummies. When D2 is continuous, it's a bit more complicated, even though it can be done. Okay, so what are going to be our target parameters? So here you see usually the way econometricians do things is that they define target parameters, and then they define identifying assumptions. And here I'm doing a very subtle change, but that would not escape most econometricians, which is that I'm doing the opposite. I'm defining an identifying assumption, and then I'm going to define my target parameter. And so what this means is that I'm starting to enter into the world that some econometricians call the world of reverse engineering, where you're not defining target parameters based on sound decision theory and then trying to estimate them, but you find reasonable assumptions that maybe you can test, and then under those assumptions you see what you can estimate, and maybe what you can estimate is not at all economically relevant, etc. But that's going to be the world that we are getting into. Okay, so it's a bit, for those of you who are familiar with this debate, it's a bit like AT versus late type of arguments. Okay, so remember that we had for non-binary treatments, the group-specific effects that we are considering are these slopes T2, which is the actual outcome, Y2 of D2, minus the untreated outcome, Y2 of 0, divided by D2. So for a group that receives 2 doses of treatment at period 2, T2 for them is their slope between a treatment of 0 and a treatment of 2. So, of course, you could be interested in many, many different slopes. You could be interested, for instance, in the slope between a treatment of 0 and a treatment of 3. And so for D2s, for period 2 doses that differ from the actual one, we are going to refer to this type of slopes as counterfactual versus no treatment slopes, while that one here, I'm calling it the actual versus no treatment slope. And so ideally, we would like to learn the entire dose slope function because, economically, that's what you need to know. For instance, if you want to determine the optimal amount of treatment that you should give to someone. So now, why is it that we don't consider that? Well, it's just that it's not that this is not economically relevant. This is certainly economically relevant. It's just that this is hard to estimate. Why? Well, that's because if I have to estimate this thing here, there is only one counterfactual outcome that's missing, which is this one. While if I need to estimate this, I actually need to recover two missing counterfactual outcomes, this one here and that one here. And now this one here, as we're going to see later, we're going to be able to estimate it under an assumption that's certainly not innocuous, but that's partly testable via pre-trans test. While to estimate this, we would need to make non-placebo testable assumption. Okay, so that's going to be why we're going to focus on this parameter rather than this one here. Now, the same argument applies to a different parameter. So you could also consider a different type of slopes where you compare the outcome under the actual treatment to the outcome under a counterfactual treatment that differs from zero, just another value. Why is that potentially interesting? Well, that's because if you let small d go to d2, then you get the derivative of the potential outcome function at the observed treatment d2, and the expectation of that derivative is sometimes called the average marginal effect, which is a parameter that has received a lot of attention in the panel data, in the causal inference literature generally. Now, you could say, okay, so here, what's the advantage of, so the previous narrative you gave me to justify why you focus on this rather than that no longer applies, because to estimate this, there as well, I only need to estimate one missing potential outcome because that one here is observed. Now, the issue is that this is a counterfactual outcome under a strictly positive treatment, not a treatment of zero. And that means that I don't observe that same potential outcome at period 1 or at period 0, etc. So if I want to estimate that, I can only do that again under assumptions that I will not be able to test via pre-trans test. So that does not mean that it's a bad thing. That just means that we're leaving the Diff-in-diff logic. And this book is about Diff-in-diff. So that's why we're not going to consider estimation of that type of parameters. Okay, and of course, we've already said that those effects are extremely disaggregated effects that only apply to one group, so we can't consistently estimate them, and instead we're going to consider more aggregated parameters, averages. And so we're going to be considering three different types of averages. One is going to be a little bit less aggregated, and the other two ones will be much more aggregated. So the less aggregated one is a functional, actually, which we're going to call the conditional average slope function. Okay, so it's the average of the TWFE across all groups with a dose equal to D2. So for instance, in my example where the treatment can take three values, 1, 2, and 3, that's we have the CAS1, which is the effect of changing the treatment from 0 to 1 among people that receive one dose of treatment. And then we have CAS2, which is the effect of going from 0 to 2 doses of treatment among people that get 2 doses. And then we have the CAS3 for people that receive 3 doses. Let's assume that you find that the conditional average slope is strictly lower at 3 than at 1. Can we conclude that receiving 3 doses of treatment generates a lower return per dose than receiving only 1 dose of treatment. Yeah, exactly. So it's, a bit related to the difficulty in interpreting variation in the event study function. We have a similar problem here, that when we move from CAS3 to CAS1, we have 2 things that change. We evaluate the slope of the potential outcome function between 2 different points, 0 and 3 and 0 and 1. And that's of economic interest. That's what ideally we would want to learn, whether, the dose-slope relationship is linear, not linear, etc., etc. But unfortunately, we learn the dose-slope relationship between a treatment of 0 and 3 for people that get 3 units of treatment. And here we learn it for a different subgroup for those that get 1 unit of treatment. And therefore, you could have that the difference between these 2 numbers could be coming from, non-linearities in the dose-response relationship, but it could come from a selection bias from the fact that people that get 3 doses of treatment are different from people that receive 1 dose of treatment. And so, of course, so now let's try to find an additional assumption under which we can indeed conclude that the treatment has diminishing returns when we have that CAS of 3 is strictly lower than CAS of 1. So we rule out what?
We have constant dose response.
Yeah, exactly. We rule out the selection bias. We assume that actually people that get 3 doses and people that get 1 doses, they are identical. Okay, and they have the same treatment effects. And so that's what we call an homogeneous slope assumption. So we're going to denote the average slope function here as, the same thing as the conditional average slope function, but where we don't condition, on the subgroup of people that got a dose is equal to D2. And then if we assume that actually, irrespective of the dose that they actually received, people that get 1 dose, people that get 2 doses, etc. So for instance, if we assume that the people that get 1 and 2 doses, they have the same average effect of receiving 1 dose, and they have the same average effect of receiving 2 doses, which is the assumption I'm stating here. Then we can estimate variation in the conditional average slope function as telling us whether the treatment has decreasing, increasing, constant returns. But that's only at the expense of making this assumption.
Sorry, a question.
Yeah.
Could we control for selection bias on observables so to make the groups with different doses comparable in observable characteristics, so this homogeneity assumption is maybe more credible?
Yeah, absolutely. So we could do that if we think that conditional on the number of observables, the people that got 1 dose are similar to the people that got 2 doses. This assumption is going to become more plausible. But you see that the spirit of those identifying assumptions becomes pretty different from Diff-in-diff. Now you're really more like in a conditionally as good as random type of identification arguments, and then but it's not. So if you're going to invoke this type of assumptions, you should put yourself in the shoes of a researcher analyzing the results of a randomized trial rather than a researcher doing a diff-in-diff analysis, which means that the specification test that you should conduct are different. Now you should not so much worry about pre-trends, but you should run balancing checks to see that you should leave some unobservables aside and control for the unobservables that you think are the most important ones, and then show that conditional on those unobservables you control for, other unobservables are the same, are not related to the dose anymore.
One issue I'm not so sure, but I'm not so sure if I would, however, make an equivalence between what we're ruling out and selection bias, because in that case, I understand the issue that you would people that get different doses have different moderators of the effect, or other factors that modify the effect. So that's why. But then you can still think that the dose has some time effect in everyone. So even if the assignment of different doses do not select on anything, then for everyone it would still be the case that those would have diminishing returns. So I'm just saying that these two different things might be interesting in different cases, and you're ruling both them out. And the selection bias may be more generally something you don't want, while the intrinsic nonlinearity of something across time may be something that sometimes you want to study.
So I think, so there are indeed two things at play here. There is the nonlinearity in the dose-response relationship, and there is the selection bias. But I think what I'm saying is that to identify the nonlinear relationship, you need to rule out selection effects.
Good.
And that's only under this condition that you're going to be able to interpret what we can identify as really giving you a dose-response relationship. Okay, and so this assumption, so it depends a bit on how the dose was assigned. If you can make an argument that the dose is as good as random, then this may hold. And you can try to back up this claim by running balancing checks and showing that people who got different doses do not differ too much on some unobservables. But if on the other end there was some self-selection into the dose, then if you think of a Roy model, it's very unlikely that this type of condition is going to hold. Okay, and so some bibliographic notes. So Callaway and co-authors, they study heterogeneous adoption designs, and they consider a target parameter that's essentially the same as the conditional average slope function up to the normalization. They highlight the fact that this type of functionals can conflate a dose-response relationship, which is of economic interest, and selection bias. And they propose what they call a strong parallel trends assumption, under which the conditional average slope function and the average slope function are the same thing. But what we want to highlight is that under the classical parallel trends assumption, which we can placebo test, their strong parallel trends assumption is actually an homogeneous effect assumption. So we think it's important to us, their strong parallel trends assumption is effectively an homogeneous effect assumption. Okay, so that's the first target. The second one is our standard ATT effect. We just take the T2s of all the treated units, and then we take a simple average of them. And then by the law of iterated expectation, the ATT is an average of the conditional average slope function. So there is a connection between the two. But then we are also going to consider a second average of those T2FX, which is going to be a weighted average. So that leading us to the Watt parameter. So the what is a weighted average of the slopes T2, where we're going to give more weight to treated units that receive a dose larger than the average dose across all the treated units. And we're going to give a weight lower than 1 to units that receive a lower dose. So for instance, in my 1, 2, 3 example, if the average dose received by the treated units is 2, then I will neither upweight or downweight the slopes of units getting 2 doses. But on the other hand, I will give a weight of 1.5 to units getting 3 doses. And I will give a weight of 0.5 to units only receiving 1 dose. So why do we consider that target, which might seem a less natural target than the ATT? So there are actually 2 arguments to do that. So the first one is convenience, in the sense that estimating this parameter might be much easier than estimating that one here, especially when we have treated units that receive a very small treatment dose, that receive a treatment dose that's local to 0. In that case, it's actually possible to show that you won't be able to estimate the ATT at the standard square root of G parametric rate. Okay, you're going to be able to estimate that parameter at a slower rate. Why is that? Well, that's because remember that the ATT is an average of those things. Only that thing here is unobserved. So we're going to need to have an estimator of that. So we're going to replace this by a y hat of 0. And then if we have treated groups that are with D2 is very close to 0, any estimation error that we make in the estimation of the missing counterfactual outcome will get divided by a very small number, which will give us an estimator with a very large variance. And eventually, we could even get an estimator that's not converging at the standard rate. Okay, and that's something that was shown in this slightly different but related context by papers by Graham and Powell and also Sasaki and Oa. With the what, we're gonna and that's an issue that's often referred to a bit loosely as a small denominator problem. Yeah, that we have a numerator with an estimation error, which we divide by a small denominator, and then things blow up. We get a large variance and potentially a slow convergence rate. Why is it that the what allows us to bypass this small denominator problem? Well, that's because the weighting, we did not choose it randomly. It's coming from the fact that plugging in the definition of T2 is this slope here, remember? Now you see that the denominator of T2 is going to cancel out with the numerator of the weights. And therefore, our what parameter, instead of being the expectation of a ratio, it's going to be a ratio of expectations. And a ratio of expectations are much easier to estimate than expectation of ratios when the ratio inside the expectation can have a small denominator. Okay, so that's the practical motivation. Now, and perhaps it's a bit of an ex post rationalization. Maybe initially we were more interested in the practical than in the economic rationalization for the what, but it turns out that you can actually give, I don't know if it's fully satisfactory, but you can give one economic rationalization for the what. I don't know if, very decision theoretic minded people would completely buy our rationalization, but it's as follows. So let's assume that you want to do a cost benefit analysis to assess if what happened in period 2, the policy that took place in period 2, which amounted to giving to units a treatment of D2 rather than nothing. Nothing was what the status quo in period 1. We want to know if that policy giving D2 instead of 0 was beneficial. Okay. And we want to do a cost-benefit analysis of that. And we're gonna make a number of assumptions. We're gonna assume that the outcome has a monetary interpretation, and or it represents units utility. No, actually, no, it's cost-benefit, so it's not welfare. So I need to assume that it has a monetary interpretation. And I'm gonna assume that the treatment is costly, and that the cost is linear in the dose. Okay, so if I want to give D doses of treatment to someone, I need to pay C times D, and the cost is known, and it's homogeneous. Like you don't have heterogeneity in the cost. Then under this simple model, you will have that the policy giving D2 instead of 0 was beneficial if and only if the benefit minus the cost of the policy, which is the actual outcome minus C times D2, is in expectation larger than the benefit minus the cost without any policy, which now is just Y2 of 0. And rearranging, you see that the policy is beneficial if and only if the what is greater than the cost of the treatment. Yeah, so it's a simple, quote unquote, I mean, I should not even say micro foundation, but like cost-benefit foundation for why we could be interested in studying the what. Okay, so now let's try to find a condition under which the two targets are actually equal to each other. Yes? Oh, yeah. Okay. So in the binary, yeah, good point. In the classical design, we don't have any distinction. And that's why, yeah, exactly. So that's also the nice thing about classical design is that target parameters are unambiguous. You cannot think of too many of that. But okay, so even if D2 is not binary, could there be a condition under which the two targets are going to be the same? So we could have that the slopes and the period 2 treatment are uncorrelated. So this is again a strong condition. It's a bit weaker than assuming homogeneous effects, like we were assuming before, but it's a little bit in the same spirit, and it's going to be incompatible with, for instance, Roy models of Roy selection into the treatment. Okay, so we've defined our target parameters. Now let's look at estimators. So like I was saying, the typical estimator that people use in this context is a two-way fixed effect, which, because we have only two time periods, reduces to YGT on group fixed effects, period 2 fixed effect, and the treatment. We are in the big T is equal to 2 case, so we have this numerical equivalence between two-way fixed effects and first difference. And therefore, the beta TFE coefficient is just the regression of the outcome change on a constant and the treatment change, but because everybody is untreated at period 1, we're just regressing delta Y on a constant and the treatment. So then can you find a simple closed form formula for the two-way fixed effects coefficient in that case? So it's a univariate regression. So we know that the coefficient on the non-constant variable is covariance between the dependent and the independent variable divided by the variance of the dependent variable. Okay? So, yeah, so we know that with a binary treatment, when we regress an outcome and an intercept and the binary treatment, the coefficient is just comparing the average outcome for the treated versus the control. Okay. With a non-binary treatment, the regression is doing something a little bit more complicated, but that still has a similar flavor. We're gonna be comparing the outcome evolution of units with a treatment higher than the average, the strongly treated units, because beta at FE, so for those, this expression here is going to be strictly positive. So their outcome evolution delta Y will be weighted positively by the regression. And for the weakly treated ones, whose treatment is below the average, they will play the role of our control group. Okay, their outcome evolution is going to get weighted negatively by the two-way fixed effect estimator. So that motivates this interpretation, which says that in an heterogeneous adoption design, the two-way fixed effect estimator compares the outcome evolution of the more and less treated groups. Okay, so I'm skipping the application in the interest of time. Yeah.
So, where is it's going to be? What needs to?
No, we're not, at this stage, we're not assuming homogeneous slope.
I mean, just make it off.
Yeah.
So the general question is why not we're interested in the different effects between treatment groups with different doses?
We could definitely be interested in that. Like the conditional average slope function parameter is looking exactly at that. But then there is just the caveat that we want to be a little bit careful in not over-interpreting that as a dose-response relationship, because this conflates response to different doses with selection. Okay, does that, yeah. Okay, and so we can show a decomposition result for the probability limit of the two-way fixed effect estimator. We can show that this estimand identifies a weighted sum of the conditional average slope function with weights that could be negative. So for instance, in my 1, 2, 3 example, if the average treatment at period 2 is equal to 2, if E of D2 is equal to 2, then this weighted sum will give a weight of 0 to the conditional average slope of those getting 2 doses of treatment, but it's going to weight negatively the conditional average slope of those getting 1 dose, and weighting positively the conditional average slope of those getting 3 doses. Okay, and so we have again this issue that in an heterogeneous adoption design, the two-way fixed effect estimator may not be estimating a convex combination of treatment effects. And so what's interesting is that there is maybe because those results on designs with variation in the dose are actually older than the results on designs with variation in treatment timing, there is a bit this feeling at the moment that issues with two-way fixed effects can only arise when we have variation in treatment timing. Here, that's an example where there is no variation in treatment timing. Everybody gets the treatment at the same date, period 2. But we can have issues with two-way fixed effects when there is variation in the treatment dose. Okay, so intuitively, why is it that the two-way fixed effect estimator could be estimating a non-convex combination of effects? Yes?
Because it uses treated people as control.
Yeah, exactly. So let's say you're comparing units that get 2 doses of treatment and you compare their outcome evolution to units that get 1 dose of treatment. Well, your units that get 1 dose of treatment, they're treated at period 2. Therefore, their period 2 outcome is not their untreated outcome. It's their outcome under 1 dose of treatment, which you can write as their Y0 plus their treatment effect. And therefore, their treatment effect gets differenced out by the Diff-in-diff. Okay, and so we can illustrate that with a simple numerical example, where here we consider it's again a silly medical example where we have 2 people that have a headache. They go see their doctor, and the doctor gives 1 ibuprofen pill to person 1 and 2 pills to person 2. And we observe that actually the headache of the person that got only 1 pill decreases more than the headache of the person that got 2 pills. And therefore, we run our two-way fixed effects, which in this case is just comparing the simple diff-in-diff, comparing the headache evolution, the pain evolution of the more treated person and the less treated person. And so we say, well, it seems that against commonly held knowledge, ibuprofen is not working. It's actually it's actually worsening the headache of people. And while in reality, it is just that we have heterogeneous effects where the response per pill of ibuprofen of the more treated patient is lower than that of the less treated patient. And that's the very reason why the doctor prescribed them 2 pills rather than 1 pill, because they could suspect that, based on their demographics and observables, that the response per pill would be lower for that person. But even trying to compensate for their lower sensitivity by a higher treatment dose was not enough, and their symptoms diminished, but less so than for the less treated patient. And that's what leads to the misleading, spurious, positive Diff-in-diff. Okay? And so here you see that related to a question we got yesterday, in an heterogeneous adaptation design, we don't need to worry about heterogeneous treatment effects across time, because in any case, here, the treatment effect only takes place at 1 time period, so it's a bit by construction. But what is a concern is heterogeneous treatment effects across units, across G. Okay, that's what could lead to a bias. Okay, and here again, if we assume that the treatment dose was randomized, then no problem anymore. Two-way fixed effects identifies a convex combination of effects. But as we said yesterday in our discussion of the assumption of randomized treatment timing, randomized treatment dose is a strong assumption that you would need to validate using balancing checks. Plus, if you're really ready to believe that the treatment dose is randomly assigned, then you should not be using the two-way fixed effect estimator. Instead, you should be regressing YG2 on the period 2 dose, controlling for the period 1 outcome. That's going to give you a more efficient estimator. Okay, so so in the few minutes left, so the last thing that we can say about the two-way fixed effect estimator is that actually, and it's a bit specific to heterogeneous adaptation designs, that would not be true in other designs, but in those designs, you can actually fully test under parallel trends the assumption that the treatment effect is linear and homogeneous, under which the two-way fixed effect estimator has no problem anymore, because, you know, if the effect is linear and homogeneous, we're fine. This assumption, which of course is very strong, is actually fully testable. And because there is an if and only if between this assumption and having that the conditional expectation of the outcome evolution given the period 2 treatment is linear in the period 2 treatment, which you could, for instance, test by running a regression of delta y on an intercept, the period 2 treatment, and it's squared, and checking if the coefficient on the squared is 0 or not. Because if it's not 0, then that means the relationship is not linear. Of course, this type of testing is a bit parametric, because, you know, let's say that the true relationship is not a square but a cubic, and then your test will not detect. But actually, there are non-parametric ways of running this type of linearity test. And actually, we're trying to popularize with Stata and R packages one nice, because there are many such tests, but most of them, you know, as in all these type of non-parametric econometrics, they rely on tuning parameters, and you don't have very clear you know, guidance as to how to choose the tuning parameter. But actually, we found one that's tuning parameter free, that's very powerful. It's a test that was proposed by Stute in 1997. And that's implemented in a Stute test. Yes, mentioned here, Stata and R packages. Okay, so now heterogeneity-robust estimators. So the type of heterogeneity-robust estimators we can use is going to depend on whether we have stayers, or we don't have stayers but we have quasi-stayers, or we have neither stayers nor quasi-stayers, which is going to be the worst of the three cases. So if you have stayers or quasi-stayers, then identification is relatively straightforward. You can show that, for instance, the what is identified by what we sometimes call a walled Diff-in-diff, a Diff-in-diff normalized by something, where we compare the outcome evolution of the treated to the outcome evolution of the untreated, which, if we assume that we have quasi-stayers, then in a sample, we will not have anyone that's untreated, but in the population, hypothetically, we can imagine that we have untreated. And then we will just scale this comparison of the outcome evolutions of the treated and untreated by the average treatment dose of the treated. Now, a nice thing about, so when you do have stayers, estimating this thing here is really straightforward. You just need to run you just need to run a 2SLS regression of the outcome evolution delta YG on the treatment dose D2, but instrumenting the treatment dose D2 by an indicator for whether someone got a strictly positive dose at D2. So instead, so there the fix to you know, like the solution to the negative weight, non-robustness to heterogeneous effects, etc. problem with two-way fixed effects is really super straightforward. Instead of running an OLS of delta y on D2, you just need to run a 2SLS of delta y on D2, instrumenting D2 by an indicator for whether someone is treated or controlled. And this ensures that this 2SLS estimator is no longer going to use weakly treated as controls. The instrument is a dummy for whether you're treated or untreated. So the controls are going to be the truly non-treated. But by using 2SLS, you ensure that the reduced form comparison of the treated and the untreated is normalized by the treatment dose of the treated. Okay, so in the case where you do have stayers, there is really no argument to stick to the standard two-way fixed effect because, you know, even in terms of, I don't know, I've not thought too much about, perhaps there are like small efficiency losses to doing that, but yeah, that could be the only argument to not move away from two-way fixed effects. Now, when you don't have stayers, estimation, heterogeneity-robust estimation is going to become much more complicated. So there, you know, in that case, the two-way fixed effect estimator might, despite its potential lack of robustness to heterogeneous effects, might still be an appealing option. And that's, I think, the interest of this linearity test that I described here, because before moving away from two-way fixed effects and trying to use an heterogeneity robust estimator, you might want to make sure that really heterogeneous effects seem to be a problem in your application by running the linearity test that we propose. Why is that? Well, that's because without stayers, even if you have quasi-stayers, you're gonna end up having to estimate, having to use non-parametric estimators, okay, which are gonna converge at a slow rate. So what's the estimation challenge? The estimation challenge is that this formula, so with stayers, we can just follow this identification result when going from identification to estimation, and we replace expectation by sample averages. But when we don't have stayers, that does not work anymore because we are not going to have any observation in our sample with a period 2 treatment exactly equal to 0. And therefore, computing a sample average of outcome evolutions for units with a treatment exactly equal to 0 will not be feasible anymore. So instead, the idea will be to use quasi-stayers, namely observations with a period 2 treatment dose very close to 0 as the control group. Now, the question becomes, okay, but how close to 0 is close enough that I can use you as a control group? When you think a little bit about it, if the threshold that you set is very high, you're going to be using units that were actually treated in large amounts as controls. So that's going to increase the bias of your estimator. At the same time, if you set a threshold that's too low, you're going to reduce bias, but you're going to increase variance because your control group is going to end up being extremely small. And now that might start sounding familiar with the standard bias-variance trade-off that there is in regression discontinuity and non-parametric estimation more generally. to choose optimal bandwidth. Okay. And that's exactly what we propose. We propose to exactly follow the literature on non-parametric estimation and RD designs in the context of heterogeneous adoption designs with in the context of heterogeneous adoption designs with without stayers, but with quasi-stayers. So the estimator is going to look at the average outcome evolution of everyone, because everyone is treated, minus an estimator of the counterfactual outcome evolution without treatment, which is going to come from a local linear regression of delta y on DG2, where the regression, the local linear regression is estimated in a subsample of units with a treatment dose below a bandwidth, and the bandwidth H will be chosen following, like results from impedance Scalar-Raman, etc., for optimal bandwidth choice. Okay, and so now with this type of estimator, we can show that they're going to be, so that's going to give us an heterogeneity-robust estimator. Does not impose any restriction on treatment effects, but the resulting estimator will not be converge at the standard square root of G rate. Is going to, as any non-parametric estimator, it's going to converge at a slower rate at the G to the power of 2/5 rate, which, you could think 0.4 and 0.5 are not too different, while in practice that's very different. And that means that typically what that means is that this estimator will have a much, much larger variance than the variance of the two-way fixed effect estimator, which is consistent at the square root of G rate. Okay, and so we've implemented our estimator in a DID, HAD, Stata, and ART packages that essentially all the heavy lifting inside the package is actually done by the NP-robust package of Canonico and co-authors. So if you end up using that package, you should also cite this package here. Okay, and finally, a very quick overview of the case where we don't have stayers. So in that case, the identification challenge is that this quantity is unidentified because we don't have anyone whose treatment in period 2 is 0 or even local to 0. And so then you can take two kind of polar approaches. The first one is to say, okay, let's not make any assumption and see if we can still get bounds for one of our target parameters, let's say the watt. So that's what we do here. And essentially the intuition for the bounds is that we're going to be using the groups with the lowest treatment dose as the control group, but that will give us partial rather than point identification, because those groups with the lowest treatment dose, they're still treated, and therefore their outcome evolution is not the Y0 evolution that we are after, but it's a Y0 evolution plus a treatment effect. But if we are ready to bound to assume that we know ex ante some bounds on the treatment effect, then from their outcome evolution, we can back out the Y0 evolution. We can back out bounds on the Y0 evolution, which are expressed here. So that's the first possibility. As with most partial identification result, a big shortcoming of this strategy. So we have an application that you can take a look at in the textbook, and you'll see that in practice, the bounds are extremely wide. So they tend to be uninformative. The second possible strategy, the other, polar solution, is to start imposing a parametric model. And one way of doing that is parametrizing the conditional average slope function, assuming that, for instance, assuming a functional form, assuming that the conditional average slope function is a polynomial in the dose, for instance, with the caveat that the assumption is hard to interpret because it's not, the conditional average slope function is not the dose slope relationship. Like you could, like if you ask a medical doctor for their prior as to the functional form of a dose-response relationship, they might have a prior on that. But that's not what we need to parameterize. What we need to parameterize is, again, the conditional dose-response relationship where there is also the selection bias term entering. And here, it's going to be much harder to parameterize this type of objects. Yes?
This. But perhaps if let's say the interaction between the dose and some other previous characteristics that may be selective and driving the bias is an interaction that, for some medicine biological reasons, is an interaction that requires mandatory positive values of all terms, including the dose, that has to be high enough. Not in that is also related to that, to how large is large.
Okay, interesting.
Some background knowledge before jumping immediately to repeating things and validating and doing machine learning and the likes, which sometimes there is scientific knowledge to rely upon about which scale. Some people maybe not.
No, especially if you have like well-documented threshold effects, whereby you have biological evidence supporting the idea that below a certain dose there is no response. Then that's going to help a lot in this type of designs.
I would expect this to happen mostly not on beneficial, actual treatments, because it's unlikely that someone thought to prescribe.
But for negative,
hazards.
No, and you're right. That's exactly in the weather literature. For instance, rather than having average temperature as the treatment, it's more like number of days where the temperature was exceeding such and such level. When they're interested in the effects on agricultural yields, because you have a research in agronomy that shows that it's only when temperature exceeds such and such threshold that yields for a given crop get. That's a good point. Interesting point. Yeah. Okay, and I think so. We are out of time, so we're gonna stop here for now. And we'll, the presentation this afternoon will be the continuation of this in any case.